Hello viewers, welcome back to my channel. I hope you are enjoying all the videos that I'm uploading. If you haven't subscribed to my channel yet, please go ahead and subscribe and also share among your friends. So today I'm going to explain the concept of tries, right? So after this, I'll be uploading several problems related to tries where the problems will be using the trie data structure. So this video will serve as a primer for the tries. Okay, so let's go ahead and look at the tries concept. First of all, trie is also a tree. Okay, so trie is also a tree, or even you can say it as a graph also, because every tree is a graph anyway, right? And there is another name for the tries. It's also called as a prefix tree. There are several applications that are currently using tries in the industry. Majority of them are dealing with strings and string searches. So for example, when you go to Bing or Google, the search engines, and start typing in the query, right, you see the search suggestions. So in major cases, the trie is used to come up with the search suggestions. Okay, so those are like some of the applications for the trie. So we are going to understand the concept of trie while we build the trie in this video. So let's go ahead and look at the scope for the trie that we are going to build as part of this video. So I'm calling it as example trie. So basically the trie example that we are going to build, it will have the scope of three things. One is it has a way to store words from a dictionary, and second is it has a way to search for a word that is already stored into the trie, and the third thing is all the words that we are storing or searching will have only the lowercase English characters, that is A to Z, right? Only the 26 letters that are there in the lowercase English letters, right? So the words will have only the lowercase. So that is the scope that we have defined for this exercise. Okay, let's go ahead and look at how the trie node we are going to define. So example trie will have a trie node with two things essentially. So there will be two variables. One variable will have end of the word denotion. Basically it will be a boolean variable. It denotes whether any word is ending a particular node or not. By default we put it as false, and the second placeholder is pointer to 26 child nodes. Why 26 means? So we have 26 lowercase letters in English, so A to Z. So there are 26 letters, that's why we have 26 child pointers to the next level of nodes, right? So hope this structure is clear. We are going to go look at the code anyway, just bear with me. And the second thing that we are going to see is so this is a structure, right? As we defined three scopes, right? One scope is it has A to Z 26 letters, right? So we have satisfied that in here, but there are two more scopes that we have defined. One is to add word to the trie, that is ability to add a word to a trie, and next one is ability to search for a word to trie. So we are going to have the two functions into the trie: add a word or string to the trie and search a word or a string into the trie, right? So these are the two functions that we are going to have. Let's go ahead and look at the trie class based on the scope and the trie structure, the picture that we saw in the previous slide here. So I'm going forward to see how the trie class is going to look like. Okay, so here is a trie class. Okay, so I'm calling it as a trie node for the class, so public class trie node, and the first variable is trie node, an array of trie node. I'm calling that as child, and word end, it's a boolean value initializing it to false by default, right? And then in the constructor, right, the child is getting initialized with 26 trie nodes. So that means any node has 26 child pointers. That is because we have 26 letters in English, right? And then as part of the initialization, right, we are going to initialize all those child pointers to null. So that is it's an important thing to do. If you forget to do that, right, it will, the trie will not operate the way that you want. In some languages, you don't have to initialize them to null because they are by default initialized to null. But in some languages, you have to explicitly initialize it to null. So that's why I'm making sure I'm initializing to null in this case, so that we don't forget, right? So let's go ahead and look at the next thing. The next things are two functions, right? So here we have already defined with a node having 26 child pointers and a word end, right? So let's go ahead and look at the functions. So add string function. So add string function will take a string. So even though we're calling it as a string, you could call it as a word, add word and string word, right? So that's not a problem. So we are going to add a string into the trie. So for this, since we are adding a string into the trie, we need a root node, assuming that we are having only one root node, because if you have multiple root nodes, you will be inserting the data into multiple tries. So just make sure you always have one root node, so that we are getting a pointer to the root node. That is what I am calling it as this. So in several languages this pointer is allowed, but in some languages if it is not allowed, right, then please refer to your documentation for the this pointer for respective languages. So here I am getting the pointer to the root node, so I'm calling it as temp. So my intention is for each character in string, right, for each character in the string that is passed, that s, I'm going to create a trie node as long as the trie node is not existing. If it is existing, I don't have to worry about it. I will go down the path anyway. So that's what it is. So I'm using get index for letter for the current letter. So when I call the letter, right, maybe I should have called character, right, get index for the character. I'm just calling it as get index for letter. So SFI. So for that character, it is going to give me the index. So what essentially we are doing is, since we are having 26 child pointers, we need to map A to 0, B to 1, and so on, as Z to 25, right? So 0 to 25 is the mapping that we want for A to Z. So that is the one. Get index for letter is the function which will do that for us. So given a letter, it will give you the index. So we are going to look at that function also. Bear with me. So if current node dot child, that particular child index child pointer is null, that means this is the first ever time we are inserting into that child, right? So if that is the case, then we are going to create a new trie node for a child, and we are advancing the temp to temp dot child of idx, right? So that is how we are going to continue inserting into the trie. And at the end of the insertion, we are going to say for the last temp, or for the last node, we will say word end is equal to true. So remember, the temp that we are setting here is not the temp that we put as this pointer, but the temp is going through the transition as part of the for loop, right? It is going down the level. So you are actually setting the temp dot word end is equal to true at the last character of the given string. So this is the add string function. And the next thing is the search word function. So we are given with a word, right, called s, the string s. Again, so we are going to get the pointer for the root node, which we are calling it as temp again, and we are going through the trie in order to find whether we have found that word or not, right? We have that particular word called s in the trie or not. For that purpose, we are going to go through each character in the string s again. So for each character, we are going to get the index. So this get idx for letter is being used in the add string function as well as search word function, so that both of them are using the same logic in order to get it right. So if temp dot child of idx is equal to null, that means you are searching for a word which is not existing in the trie. In that case you will say okay, I don't have this word, so you return to false. Otherwise you continue on to until the length of the string s. So once you reach to the string s, what you are going to see is the word and at the temp is true or not. So if it is not true, you are going to say okay, return temp dot word end, whatever the word end value there it is, you are going to return that. So if the word end comes, that means you found the word which is existing in the tree node, but otherwise it is not existing in the tree node, right? So that is how the two functions add string as well as the search word functions will function. Okay, and let's go ahead and look at the helper function get idx for letter, right? So this is a very simple code. What we are doing is, for a given character we are subtracting a from it. Okay, so that means we are transforming, if the character is a, we are transforming that to 0. If the character is b, we are transforming that to 1. If a character is c, we are transforming that to c minus a, that means 2, right? So the character, even the character variable name here c, I'm referring to the real character c. Okay, if the character is d minus a will be 3. Okay, so likewise we are going to use this get index for letter. So these are the essential functions that we need. So please go through this video multiple times to understand the trie class and its functions. This is the basis for the problems that I am going to upload based on the tries. Once you get good understanding of the tries, we will be using similar methods like add string or search word in a similar way, not exactly the same way, but in a similar way we are going to use as part of the problems that I am going to upload very soon. If you have any questions on the tries concept, please leave your comments in the comment section below. Again, if you haven't subscribed to my channel yet, please subscribe to my channel and share among your friends. Also, don't forget to click the bell icon. If you click the bell icon, you are going to get all the future video updates from me. Thank you for watching again. I will be back with another video. Thank you. Thank you very much.